My name's Bill Tainsh. I'm from Mostyn Enterprises, Sydney, Australia. Our company specialises in doing unusual things in the RF field. Our prime area of interest is HF, VHF, UHF, or for comms guys 1 to 512 megs. We look at problems between the back of the radio, the output of the RF signal, to the antenna. To some of you might say, oh, that's just a bit of cable. In this modern army, it's not. It's a lot more because the army is pushing the technology. So what I'm going to be talking about today is a problem that the army has various names, but basically that when you have a radio transmitting from one antenna, it can interfere with a radio receiving on another antenna. So we've developed a matrix switch which looks at, these are the common specs here. As you can see, we can do the switch in many different variations. Our technology is designed for adaptability. This is a block diagram of a very simple non-intelligent switch, user-operated. It doesn't solve any problems, but it gives the operator the ability to switch radios to different antennas if required. This is our standard matrix switch. Now what we've done here is taken the basic switch, we've added some intelligence to it so we can measure certain signals, and we've developed an algorithm to look at this information and make decisions to switch the radio to a different antenna where there is a conflict between it and an adjacent antenna. The purpose of this is to get maximum distance between antennas to reduce the potential of interference. We measure the power out, we measure what's called return loss. In other words, that is a signal that is reflected back into the radio or the power amplifier. Now, modern solid-state amplifiers are very intolerant to signals being fed back into them, and if you're not careful, you lose your radio. It goes bang. Cost $500, $2,000 to repair, but you've lost your radio until you get a replacement. So that's solved some of your problems of selecting which antenna is best for which radio based on frequency, power, and other considerations written into the algorithm. So you can see that the standard switch has developed further from the basic switch. We now come to the advanced switch. This one is taking it up another level. That we all know what army drivers are like, don't we? Has anyone been in the army and driven a vehicle? No? Well, I can assure you they're not exactly kind to radio masts sticking up on the top of the vehicle. They run under low branches, they go through heavy scrub, and antennas have a bad habit of getting snapped off. The modern radio does not like it. So you've got to take urgent action to resolve the problem. So what we do is switch that radio off to a dummy load, so it's looking at a good signal. As far as the radio is concerned, it's working properly. We recalculate all the radios so as to select which is the best solution for all the radios to operate on, instead of 4 antennas, 3 antennas. We can also work it down to 2 antennas. If 2 antennas on one side of the vehicle are taken out, we can transfer those radios on that side to the other side by using what's called a combiner. The name says it all. Then when we've completed our reconfiguration, we then switch the radios to the appropriate antenna. The soldier driving the vehicle, who's usually also responsible for the equipment, is given an alarm is raised to tell him he has a problem. He identifies it from a control panel. He then, when an opportunity presents himself, pulls over, replaces the damaged antenna, sends an instruction, now fixed, and the system then goes back and looks at it all and says, yes, I'm happy with it. I will now reconfigure back to the original configuration. If, for example, the Army changes the frequency that radio is working to another one, the switch sees the change of frequency, recalculates and reconfigures. We're also starting to work on a intelligent bandpass filter. Now this is a filter that you can say that the radio will transmit any signals between the high and the low sides of the filter. We will have one before long that will look at the frequency and dynamically change the filter so the frequency being transmitted by the radio is in the centre of what we call the bandpass. When the radio manufacturers progress to the next stage, we'll be able to link this filter to the radio, so when the Army uses the radios in what's called frequency hopping, the filter will be able to follow the radio because it's been told by the radio that it's changing frequency to the next nominated frequency. So, summing up, Mostyn Enterprises look at problems or potential problems, go away, think about it and come up with a solution. Thank you. Any questions?
Excuse me. Sir, do you have a product available or a prototype that has been validated?
No, we go into the mechanical mock-up design in 1 week from this Sunday, your time. The individual modules have all been tested. We're now into integrating the products into a single vehicle mount housing.
And then that would be designed for each of the different type of radios?
No,
tailored
it's
smart.
It's irrespective of radio.
Okay.
So whether it's Harris, Talus, Roden Schwartz, it doesn't matter whose radio it is, we don't care.
Okay,
it's independent of the platform. It's also independent of the antenna.
Is it also band agnostic?
Say again?
It can handle any kind of bands, whether it's X-band or KU?
The system is aimed primarily at the HF and tactical area, that is 1 meg to 512. However, we go up to using TNC and SMA connectors to 12.5 gigs, and if we use SMA, we can go to 26.5 gigs.
Thank you.
Oh, and incidentally, HF can go to 5 kilowatts and 1 gig's 300 watts.